Hello, my dear students. So we are opening Unit 4 of General Physics 1 this afternoon with the topic on work, energy, and power. So the trio of work, energy, and power. In this segment or in this portion, we are first going to talk about work and power. So talking about work first. So in physics, work has a very specific definition, different from uh, its definition in the English dictionary. So when we talk about work, there has to be a force acting on an object, and that force should be responsible for the object being displaced in the same direction as that force. When that happens, it can be said that the object received work or work was done on that object. We can express work in equation form. In symbol, work will be W, capital W, and it will be equal to F for force multiplied with change in x or change in position or the displacement. So work is just a product of the force and the displacement experienced by the object. If that is the case, the unit of work will be the product of newtons and meter. So the combined unit is actually joules. Joules in symbol is the capital J. So here are some examples of work. A horse pulling a plow through the field. So the horse is pulling or applying force, or the plow is experiencing an applied force from the horse. And let's say the applied force is to the right, and the plow is being displaced as well to the right or to the east direction of the field. You would say that the plow, our object of interest, is experiencing work, or there's work acting on the plow. A father pushing a grocery cart down the aisle of a grocery store. So the object of interest here is the grocery cart. The cart receives applied force from the father and it is displaced in that particular direction, in the same direction as that applied force. So work is done on the cart as well. A freshman lifting a backpack full of books upon her shoulder. So in order to lift the backpack full of books, the freshman has to apply an upward force on the bag. As a result, the bag is displaced upward from a lower height to the height of the shoulder of the freshman. So work is done as well on the backpack. A weightlifter lifting a barbell above his head. So same scenario as the third one. Applied force is done on the barbell and it gets displaced upward as well. So work is done on the barbell. Non-examples of works. So sometimes you might be applying force on an object, but it does not necessarily mean that work is done on that particular object. An example being this one, the tray. A waiter is exerting an upward force on the tray as he is carrying it across the restaurant. So in order to lift the tray upward, so the waiter has to exert an upward force on the tray through his hand and arm, right? But if you think about it, the waiter keeps the tray level, maybe along his neck, right? So it's not moving upward or downward, while the waiter is moving across the restaurant. Maybe if he is serving the food, he would lift it downward and upward to carry some other, let's say, glasses on empty tables. But as he is moving across the restaurant, the tray, of course, moves with him, right? But it is not the upward force that is responsible for doing that, for that particular displacement, for that particular movement. Okay? The upward force is done in order to lift the tray and to keep it level. But since the waiter is walking, the tray moves with the waiter, but it is not that particular upward force responsible for that displacement. So therefore, we will say that that upward force is not exerting work, or no work is done on the tray by that upward force. Here's another example. A man is pushing on an immovable wall. So pretty sturdy wall, right? So even though you are exerting a large amount of force on the wall, but if you are not capable, or if you are not able to displace or to move the object, in this case the wall, no work is done on that object. Okay po? So work, you can be exerting positive work or zero work on an object. So of course you can also give negative work, or negative work can also be done on an object. Here are some examples. Leftward friction will do negative work on an object that is accelerating to the right. So in our previous example, a father was pushing or applying force on a grocery cart to move it forward. So the applied force is um, doing positive work on the cart. But remember, since the wheels of the cart is moving across a surface, the floor of the grocery store, there would be friction exerted on the cart or experienced by the cart. So the frictional force will be the one doing negative work on the object, since it is not facilitating displacement, the forward displacement, but actually inhibiting it or slowing down to some degree the forward motion of the cart. Okay, so there are two horizontal forces present. One is the applied force causing the positive work, another is the frictional force, but the frictional force is causing negative work since its action is opposite the displacement. The downward gravitational force will also do negative work on an object being lifted upward. So just like our example with the barbell being lifted above the head of the lifter, so the upward force is causing, yes, positive work, but the gravitational force, remember, which is always downward, the gravitational force is causing negative work on the barbell. Let's use our formula for work on some sample problems. So in the first one, we are asked how much work is done by a power lifter that pushes a car with a force of 80 newtons, or 800 newtons rather, at a distance of 200 meters. So again, our formula is work equals force times the displacement. So here we specified the force as being the applied force. And we had a displacement of 200 meters. Multiply that with the force applied, 800 newtons. Newton times meter is joules. Therefore, the work done by the power lifter is equivalent to 160,000 joules. Or you can express this in terms of kilojoules. Just divide this by 1,000. Okay? It would be 160 kilojoules. Here's another problem. How much work is done by the force of friction? Okay, force of friction, meaning to say it's doing negative work. If a man pushes a refrigerator across the floor with a distance of 1.2 meters and a 350 force of friction that opposes the motion of the refrigerator. So our formula will be force times displacement. This time, we specified force being the frictional force, and we already put a negative sign right there on the frictional force, since we know that it's causing negative work on the object. So negative 350 newtons times 1.2 meters, Newton times meter will be joules. The work done by the frictional force on the refrigerator is 420 joules. Here is the next term, power. So power will also have a specific definition here on Unit 5. The rate at which work is performed, or work per unit change of time, is defined as power. Meaning to say, work per unit change of time. Work divided by the change of time. Work divided by time in equation form. So power is will have a symbol capital P that will be equivalent to capital W divided by change in time, or divided by time. Machines that we have in our homes will have power rating in their labels, right? If your machine has a high power rating, if your engine has a high power rating, that means it can perform work very fast. Since work is the rate at which work is done, if you have a high power rating, relatively fast, it can perform whatever work it is assigned to do. The unit of power is watts. Also in W, don't get it confused with work. This is after James Watts. So since work is in joules and time is in seconds, the SI unit is watts. Joules over second is watts. Please, again, do not confuse it with the symbol for work, which is W. Here's a sample problem. Determine the power of a heavy equipment that performs 55,000 joules. Or if we divide this by 1,000, I think it should be 55 kilojoules if you divide it by 1,000 in 1.1 seconds. So very fast, ano? Approximately or around 1 second, it can already perform this much work. So power will be equivalent to work divided by time. Work is 55,000 joules in our example, divided by 1.1 seconds. That's the time. So if we divide the two, what will be getting is 50,000 watts. Or if we want to express this in kilowatts, we just divide by 1,000. So 50 kilowatts. Here's another example. Determine the power performed by a 60 kilogram man running up the stairs with a height of 4.5 meters. 4.5 meters is the height of the stairs, not the man, in 4 seconds. We have some hints here on how to solve this problem. So meaning to say, you can also compute for the power of a human person, not only those of a machine. Let's analyze this example a little bit more. So power can be computed using work over time. So time is given here, 4 seconds. The man has to climb the stairs, or the man climbed the stairs in 4 seconds. Now, our problem is, how do we compute for the work? And what's the object of interest in this type? So what we want to do here is for the man to lift himself from the bottom of the stairs to the top of the stairs. The stairs has a particular height, 4.5 meters. In other words, the man has to displace himself from 0 meter to 4.5 meters. So we already understand our displacement. Now, how do we compute for the force? How much force do we need to have here for the man to lift himself up, to run to the top of the stairs, if the stairs has a height of 4.5 meters? So the question is, how much force do you have to exert on yourself to lift yourself up if you have a mass of 60 kilograms? So in other words, you want to determine your weight. Your weight is 60 kilogram times acceleration due to gravity, 9.8 meter per second squared. Kilogram times meter per second squared is newtons. So what we have is a weight equal to 588 newtons. This means that your body has to counter your weight. Your weight is directed downwards, right? So you have to counter this weight. You have to give yourself an upward force equal or greater than 588 newtons. Let's go for the minimum here. So let's say equal to 588 newtons. So your work that you have to apply on yourself is force times displacement, 588, times the height of the stairs, 4.5 meters. So if we get the product of the two, that would be 2,646 joules. How fast did the person do the work? We can power. 2,646 joules divided by 4 seconds. Joules divided by seconds is watts. And the division will be 661.5 watts. Okay.